All right, so we cannot take the square root of a negative number. We can take the square root of 0. What is it? 0, square root of 1. There we go. Stop spinning. If that's 0, 0, 1, 1, and 4, 2, what do you think? What's the next perfect square? 9. What's the square root of 9? And what's the next one? And what's the square root of 16? 4. So if we had 9 on this graph, it'd be at 4, and then 16 would be at 5, and then 25 would be at 5, and then 36 would be so on and so forth. And so it just continues to get bigger and bigger. Making the domain what, Sierra? What will be the domain if you look at this graph? Oh, careful. Remember, domain relates to which axis? X or Y? X. And we notice, remember, we couldn't take the square root of any negative number. So we start at 0 and go to positive infinity. And so 0 is included. What about the range? What about the range? Think about it. Range relates to which coordinate axis? The Y. Look at your Y. Okay? I mean, we went over, at 9, we're at 3, and 16, we're at 4, and 25, we're at 5, and 36, we'll be at 6. It's going to keep on going up and up. It's going to do the same thing. There are no negative y's at all in our range. But what about my intercepts? Where does it cross the y or x axis? At 0, 0. And what do I mean when I say intervals? What do I mean when I say intervals? Jamie? Where it's increasing and decreasing. If we look at this function, what's happening? It's increasing from what to what? 0 to infinity. And there you go. There's the next parent function. We've been dealing with parent functions since yesterday. Okay? There are 8 of them. You need to commit this to memory, okay? Some of these properties, some of these features, domains and ranges, everything will make your life a little bit simpler when you're answering questions the further we move forward, okay? The next one, cubic functions. I give you a table, fill it in, get the graph, okay, of this cubic function. Make sure you're also writing down what exactly the parent function is, okay? Make sure you're writing that down as well. So complete the chart and graph it. When x is -2, what's y? -8. And even though -8 wasn't on your graph, it's still, you can still kind of guesstimate where it would be. At -1, -1. At 0, at 1, and at 2, 8. So it basically makes this curved little figure here. And it continues, okay? Because you can do 3 cubed, and you can do -3 cubed, and it would just keep getting bigger and bigger. Which means that its domain would be what, Henry? What would be its domain? -infinity to infinity. And its range, Chris, what would it be? -infinity to infinity. Yes. So, the same for the domain and range, okay? If you ever forget this information, just remember domain is x, range is y. Look at the graph, see what's happening. There are no gaps, holes, asymptotes. Any area that's not undefined is, all real. Intercepts. Where's the cross? Where's the cross, Siege? Where's the cross? 0, 0. X and Y. Same. Intervals. What's happening? I read from left to right. Not on the intercepts, that's the actual point. So those will always be parentheses. Only time you have to worry about the interval brackets is when you're doing domain and range. Huh? What's happening from there to there? Okay, so what's happening before 0? Not decreasing. Remember, we read from left to right. So if I'm reading from left to right, I'm coming from down here. I'm coming up. Going up. Increasing. from negative infinity to positive infinity. Up, up, and away, okay? Going up the entire time, increasing. And I do have some symmetry here. Should be able to recognize this. It's origin symmetry, because what type of function is it? It's odd. What other parent function have we gone over that also has origin symmetry, making it an odd function? The reciprocal. Okay, the reciprocal function is also symmetric about the origin. Okay? So we're almost done. We got 2 more to do. Which one do you think we're doing next? No. We're going to do quadratic next. Okay, greatest integer is something I don't think anybody has seen in this class, in any classes they've been at Lake Wales High School for the whole math time. Here we go. So, quadratics. Y'all should know this. What does this graph look like? A parabola. A parabola is in the shape of a what? And a U. And when you plug in 0 into this, you end up at 0. That point is known as what? The vertex. Yes, it's known as the vertex. And because it's positive, does it open up or down? Where are you from last year? Opens up, making the point 0, 0 a what? Absolute minimum. Okay, remember extrema that we talked about in this class? There we go. When I plug in 1, what do I get? When I plug in 2, and when I plug in 3, what would it be? 9. So it keeps going up. If I plug in -1, what do I get? And -2, 4, and -3 equals 9. So it's just going to continue to go up and up. Please concentrate on your graphs. Remember, these are your notes. So you want your graphs to look really nice. Mine might not look as such. I mean, it's like usually when you're like straight above it versus looking at it and taking it up to the side, so I ain't like. So right here, you can already tell me, you know I want to ask the same 2 questions. What's the first one?
Right.
Who can give it to me? Martha? Negative infinity to infinity. The next one is? Range. 0 to infinity. Is 0 included? 0 is included, so it needs that square bracket. Looking at this, what are my intercepts? 0, 0. And what are my intervals? My intervals. I ain't trying to avoid eye contact with me. It's like, wait, hold on, let me see. Who knows the intervals? It's increasing where? From what to what? Careful. Which one? 0 to infinity is increasing. And what's happening from negative infinity to 0? It's decreasing. Last but not least, is there symmetry? Yes, and it is the y-axis, making it what type of function? Even. Good. Did I cover everything? I think I did. So, negative infinity to infinity, 0 to infinity, 0, 0. Where was it increasing again? I forgot. I didn't about to see if y'all were paying attention. 0 to infinity, and it's decreasing where? Symmetry, we said it was y-axis, making it even. I talked about the vertex. Where was the vertex located?
0, 0.
And what type of extrema? There you go. So we covered all that. The last type of function that we're going to talk about, I'm pretty sure that you guys have never seen before. It's called the greatest integer function. Are you guys ready?
Yes.
It's not hard, it's different.
Whoa.
It's different. It's known as your step function. Okay? Alright? What's around the x is the symbol to let you know this is the greatest integer function. And I know it's kind of hard to see, so it kind of looks like this. It's like a square bracket with an extra line in it.
Oh, that's just strange.
Okay? So when you see this, this means greatest integer function. Okay? So go ahead and take a second to get that graph down, and I'll talk about it a little bit before we go to some of the projects. So your greatest integer function is known as your step function, because if you look at this graph, it doesn't look like a set of steps.
It looks
Alright.
strange.
Yeah, it does look a little strange, but it's unique in its own way. Okay? It's unique in its own way. It's defined on the left part of each step and undefined on the right part. But just because it's undefined here, it's still defined on the function itself. Okay? So do keep that in mind. That even though it's undefined here, it's still defined right there. And honestly, how would you use the greatest integer function, like if you were to evaluate it? It's actually very simple. So say I asked you to evaluate on this function f of negative 3.5. Well, negative 3.5 relates to x. So if I went to negative 3.5 on my x-axis, I see that it hits the curve right here. What's the corresponding y value when x is negative 3.5? Negative 4. Okay? F of 2.5, or actually let me see, f of 2.3. 2.3 is located right after 2. What's the corresponding y? 2. Okay? That's all you do to evaluate the function. It's kind of like it's almost kind of like rounding, but you're going towards an integer. All your answers will be integers every time you evaluate, okay, on the greatest integer function. Hence why it's called that. Yes?
How do you know it's those points?
How do you know it's those points? Well, the fact is that it's your function equals x, except it's that integer function. And so you would know that if x was 0, it's defined at 0, and then you go over to 1. Like, it kind of tells you, like, where's your defined point, and then you know it goes over 1 unit, and then it's undefined at that next unit over. Okay? What if I asked you f of negative 1? What would you tell me? It would be negative 1. It wouldn't be negative 2 because it's undefined there. It's defined at negative 1. Okay? So just be cautious if you ever had to evaluate that. Now let's review some of these properties. Domain. It is, say it again, negative infinity to infinity. Because again, even though it's undefined here, it's still defined here. Even though it's undefined at 0 and negative 1, it's still defined as 0, 0. At no point in time is an x value undefined. It's always defined. But your range is what? No, it's not going to be negative infinity to infinity. It's not undefined. Huh? What numbers? The numbers in the y? Keep going.
So like if it were negative 1,
It'd be negative 1. And if I was at negative 2, it'd be negative 2. And then negative 3, and negative 4, and negative 5, and negative 6, and 0, and 1, and 2, and 3, and 4. All of those numbers are what types of numbers? Integers. So it's all of my integers, isn't it? It's not negative infinity to infinity because I'm not defined in between like 0 and 1 or 4 and 5. It's only my integers. So you write that like so. Okay? Y is the set of y such that y is an element of an integer. It can only be integers. Okay? And it's not like we would sit there and we would list out every integer. That'd just be silly. But you can represent it nice and neat in set notation. We would not be able to use interval because interval notation includes a range of numbers. We only want specific integers. Your intercepts are there as well. And when you think of increasing, decreasing, or constant, it's only constant between each pair of consecutive integers. What does consecutive mean? Consecutive. What does that mean? SAT word. What does that mean?
repeating.
Not repeating.
Right after each other.
Right after each other. One right after each other. Okay? And it vertically jumps 1 unit at each integer value. Because now we're going to transform all of our parent functions. Here we go. Just a few notes on transformations, and then we'll get to the focal. So talking about transformations, you kind of, if you had me for geometry a few years ago, then we would have done a few transformations with those two-dimensional shapes. They still apply here. You have rigid transformations and non-rigid transformations. Rigid transformations, you change the position. In other words, you change location, okay? And you can change the location by either moving left and right or up and down. A non-rigid transformation distorts the shape of the graph, which means that it's either going to get skinny, bigger, flatter, wider, it's going to shrink, get narrow. Basically, the size is going to change. And then you have these three types of transformations. You have translations, reflections, and dilations. Translations, what's like the more simpler word for transformation? Translation.
Slide.
A slide. Okay, so translation means slide. And I can slide a curve what ways? To the left or to the right, up or down. Now, reflections is a flip. Okay? Like a mirror. It's a reflection. Okay? So reflections are flips. Lastly, dilations. What's a dilation? Make it smaller or bigger. Think about it. When they dilate your eyes, when you go for your eye exam, your pupils get bigger. Okay? So dilations are either going to make you bigger or smaller. Narrower, or wider. Narrower or wider. All right. And out of these three transformations, which one of these is a non-rigid transformation? It's a dilation, because only dilations change its size. Okay? Translations or reflections just move this location, but it does not change the size. Okay? And so we're going to talk about all the different types of transformations there are. Okay? So let's start off with your translations. Okay? We're going to start with your vertical shift up and your vertical shift down. Now in this case, K represents any constant. Okay? Any whole number. So Fs represents your function, and if you add a number to it, you're shifting that entire function up. And here's an example of that. Your parent function of x squared, and you have x squared plus 2. Well, first off, what type of parent function is this? Which function was it? Quadratic. I'm going to take that parent function and move it up 2 units. That's a slide. I'm not changing its size, I'm just changing its location. So that means that every point that's on that original parent function is going to be up 2 units. So the point that was at 0, 0 is now going to be where? 0, 2. It got moved up 2 spots. That point that was at 1, 1 is now going to be where? It moves which way? Up 2. So it's going to be now at 1, 3. The point that was at 2, 4 is going to be where? 2, 6. I move up 2 units, and I can do that on the other side. Negative 1, 1 is going to be where? Negative 1, 3. And negative 2, 4 is going to be where? Negative 2, 6. Okay? Yes. You're writing this on the pink sheet. These are the examples on your pink sheet. Okay? So all your transformations and example will be there for you. Okay? And so it doesn't change its size, it just changes location. Now when I move it up 2 units, which coordinate out of my points was affected? The x or the y coordinate?
Y.
The y. So a vertical shift affects your y coordinate. Okay? So that's another way you can do all these transformations. You can use the points, and then you can adjust the points accordingly. Okay? Minus k means the exact same thing. You're going to move the whole function down. Here's another example. You have the square root of x, your parent function, which is shown, and then you have the square root of x minus 1. That means that every point on this parent function is going to move down 1. So 0, 0 is now going to be at 0, negative 1. 1, 1 is now going to be at 0. 4, 2 is going to be at 4, 1. Everything got moved down 1 unit. Everybody see that?
Yeah.
Okay? And thus, those are your vertical translations. Okay? Move up, down. Plus K, minus K. Okay? Now don't be confused with the horizontal translation. Okay? If you notice, the constant now is inside with the x. And if it's a minus, you're not moving to the left, you're moving to the right. And if it's positive, you move to the left. Okay? Do you guys see the difference between being on the inside versus being on the outside? Okay? That's how you'll be able to distinguish if I'm moving left or right versus up and down. Okay? So right here, the absolute value function means I want to move this original parent function, which way? Right, how many? 2. So when I move to the right 2, the point 0, 0 becomes what? 2, 0. 1, 1 becomes 3, 1. 2, 2 becomes 4, 2, and so on and so forth. Every single point gets moved over 2 units. So you can use the graph of the parent function and translate it, or you can take the ordered pairs and alter them. Okay? If I'm moving to the left or to the right, which coordinate is affected? Is it the x coordinate or the y coordinate? The x. So you can just keep that in mind. You don't have to use the parent function to draw this. You can always use the points. And you don't always have to use the points to draw it. You can use the graph, okay? You gotta know what the graph looks like. That's why you need to commit all those parent functions to memory. So that way you can alter them whenever you need to. Does everybody understand that? Cool deal. Plus means I'm moving to the left. So that means everything is moved to the left 2 units on this quadratic, okay? So move 2, move 2. Okay? Make sure you guys are doing that. It doesn't change its size, it just changes its location. Okay? How do you know the difference? The first one, the negatives on the outside is a reflection across your x-axis. The negative on the inside is a reflection over your y-axis. And if you ever get confused, what does f of x mean? And in the very first case, I'm making my y's negative. Well, the only way to make my y's negative is to flip it over the x-axis. Does everybody see that?
Yeah.
Here, this one right here, my x's are negative. The only way to make my x's negative is if I flip it over the y-axis. So that's a good way to, remember if you ever get confused between the two. Okay? This, I make my y's negative, that's x-axis. Here, I make my x negative, that's my y. So I'm going to flip my parent function over the x. If I'm on the x-axis, does the point change? No. But this point of 1, 1 becomes what? 1, negative 1. This point here at 4, 2 becomes 4, negative 2. So if I reflect it over my x-axis, remember I make my y's negative. And all my y's negative? There it is. The next one reflected over my y-axis. 0, 0 stays. But 1, 1 turns into what? Negative 1, 1. 4, 2 becomes negative 4, 2. So when I reflect it over my axis, my y-axis, my x's became negative. See how it works there? Questions on your reflections? Now, the last 4, they're similar, but they can be tricky, okay? Starting with my vertical stretches and shrinks. Now when I'm talking about stretching vertically, I think of it as me pulling from the bottom and the top and pulling up and down. Okay? That's a stretch. Okay, a shrink would be me pressing it down. Okay? Try to imagine me pressing it down. I'm shrinking. Okay? That's what's going to happen to these graphs. You'll know the difference between a vertical stretch and shrink over a horizontal is where the number is located. If it's on the outside of the function, it's a vertical, and when it's on the inside, it's horizontal. You'll see horizontal in just a second. If this number is greater than 1, I'm stretching it. Okay? And it's going to be times 2, but which ordered pair is going to be multiplied by 2? Is that my x's or is it my y's? It's your y's. Because think about vertical. The vertical axis is y, so my y's are going to change. Okay? So, just a quick recap. If you want to write this down, I would probably say write it down in the white spaces that are off to the side. Here are the points of my absolute value function. The original parent function points. When I vertically stretch it, I am multiplying all of my y's by 2. So 0, 0 will stay the same, but 1, 1 will become, careful, 1, 2. Negative 1, 1 will become 2, 2 would be, and negative 2, 2 would be. And when you plot those points, you will see 1, 2, 3, 4. My graph has been vertically stretched, also known as getting narrow. The shrink does the opposite, okay? And you notice a shrink if A is between 0 and 1, such as this example, 1/4. That means all my y's are now going to get multiplied by 1/4, okay? Are you guys okay? You guys have any questions so far? You guys have any questions so far? A lot of what you guys did last year was just move it left, right, up, and down, or flip it. But see, we only did it for quadratics. We're doing it for all of them. Okay? I'll do the same thing. I was a 0, 0, 1, 1. I think it was 2, 8 was the next one. And then negative 1, negative 1. Those are the original points on the parent function. I'm going to shrink it now. That means that all of my y's are going to get multiplied by 1/4. So 0, 0 will stay the same. But 1, 1 would turn into what? 1 and 1/4. 2, 8 would be 2, 2. So I'm multiplying all of my y's by 1/4. This would be negative 1, negative 1/4. And this would be negative 2, negative 2. So when I plot it, you see it's been shrunk. Okay, I'm pressing it in, which essentially is making it what? Wider. The last two, horizontal shrink and horizontal stretch. Okay? A horizontal stretch, as you see what I was talking about, you know it's horizontal if the A is on the inside or the number's on the inside. You see the difference? And your stretching is when A is between 0 and 1. Okay? Here's how you'll be able to tell there. Okay? Here's another example. If A is greater than 1, that means it's going to shrink. And it shows you here what that would look like. Okay? Now, one thing you have to be aware is that horizontal shrinks and stretches relate to vertical shrinks and stretches. A horizontal stretch is the same thing as a vertical shrink, and a horizontal shrink is the same thing as a vertical stretch. Okay? Because think about it, I'm no longer pulling from the top and the bottom, now I'm pulling from the left and the right. So when I stretch horizontally, vertically, I'm making it wider. But when I shrink horizontally, vertically, I'm making it narrower, aren't I? Okay? And so to figure this out, graphically, you wouldn't be able to tell if it's a vertical stretch or shrink. You would actually have to look at the function to determine that. Okay, so keep that in mind. All right? But you can still figure out the points here. Okay? Because it's attached to the x here, we're going to affect our x's. We're going to change our x's. But we're not going to multiply it by 1/4. We're going to multiply all of our x's by 4. It's always the reciprocal. It's always the reciprocal when you're dealing with horizontal shrinks and stretches. That's the only way that you're going to horizontally stretch this parabola. So real quick, if I multiply all of my x's by 4, that becomes 4, 1, 8, 4, negative 4, 1, negative 8, 4. I took the points of the parent function. Oh, y'all, don't plot it yet. Don't plot. See, y'all about to copy me, y'all about to make a mistake. 4, 1, sorry. I was like, something's not right. So 4, 1, 8, 4, negative 4, 1, 8, 4. You see what this one looks like? It's a horizontal stretch, but think about it. If I was pressing at the top or the bottom, wouldn't it flatten out? It's a vertical shrink. So that's what that would look like, real roughly.
You press it at the top of the line?
Yeah, so like
not like actually the whole top of the graph.
Like if I was taking the curve, not the graph itself, but if I was taking that U and I was pushing down on its endpoints, that'd be vertically shrinking. But if I was pulling that curve, it would make it.
I just don't see how like the middle just doesn't like go from this to like.
What do you mean the middle goes from?
Okay, so